In this video, we will learn about circular motion. In the previous video, we learned about further momentum. We completed this entire subchapter or chapter on momentum. So the topic is further mechanics. This is from the Edexcel IAL Physics syllabus. So let's go through this and we will try to complete this in this lesson. Okay, so let's scroll down. Now that is actually unit 4. So in the IAL, that is the second year, you have IAS and IAL. So units 4, 5, 6 are under IAL, and under IAL you have units 4, 5 and 6, and now we are doing the content in unit 4. So for more information you can go through your syllabus, and once I arrive, yeah, so we have completed all this. Okay, now this is where we start chapter 6.2. Okay, I'll also show it to you from your syllabus. This is your Edexcel IAL Physics syllabus, and you can see this is unit 4, further mechanics. Make sure you go through all this, because in this way you will have idea of what you are supposed to learn and what you're supposed to know for the exam. Now in the previous video we covered momentum, so we have basically covered all this, and now we are starting from here, because from 87 onwards all the way to the end is circular motion. So make sure we complete all this. Now once we do it, you will see that we will be covering all this, but let me briefly go through it so you can do this by yourself also. Before the lesson starts, go through this syllabus, your syllabus, and ensure that all these topics are going to be covered. And once the lesson is completed, again go through this and ensure that all of this has been completed. So you have to do that for every lesson, and finally once you finish everything, again you can go through and check whether everything is complete, so that you know you have learned everything that you are required to know for the exam. Be able to express angular displacement in radians and in degrees. Now there are 2 units of angles that you are supposed to know. One unit which you have learned even in the O-level or Edexcel 9-1 classes is the unit degree. Now we have another unit, that is the radian. Okay, 2 pi radians is equal to 360 degrees. You should be able to convert between these units, so we will see them. And it's very simple. So you can say 2 pi radians is equal to 360 degrees, or you can say pi radians is 180 degrees. So once you have that conversion factor, you can convert from any value in degrees to any value in radians, or the other way. Now what is angular displacement? We will see all that. Understand what is meant by angular velocity. So you have learned velocity equals displacement divided by time. Similarly, angular velocity is angular displacement divided by time, and displacement, velocity are both vector quantities. Time is a scalar quantity. And we have some equations here. Then you have this another equation that has the acceleration. We call this acceleration centripetal acceleration. So you would have learnt in the Edexcel 9-1 or O-level classes that anything that is moving in a circle or a circular path, even if it is moving at a constant speed, will have a resultant force acting towards the center of that circular path in which it is moving. This resultant force is called the centripetal force. So if there is a resultant force, there has to be an acceleration, because it is the resultant force which produces the acceleration. So there has to be an acceleration because there is a resultant force, Newton's second law, and this acceleration is what we call centripetal acceleration. Understand that a resultant force, now in this case if it's moving in a circle, that resultant force you can say is towards the center of the circular path, and if it is towards the center of the circular path, then definitely that will be a resultant force, and to be very specific, that is called centripetal force, because this force is required to produce a circular motion. Then using f equals ma, now you remember this equation, you have learned it in the O level and the Edexcel 9 to 1 classes. This f is always a resultant force. This is the Newton's second law equation, f equals ma. The resultant force is equal to mass times the acceleration. From this we can get the equation for centripetal force, which will be this and this. Now remember, a is equal to v squared over r. This is the centripetal acceleration. So if we substitute that here for a, we will get mv squared over r, which is what you see here, and that is actually this one. Similarly, if you substitute, now this is one equation for centripetal acceleration and this is the other, r omega squared. So if you substitute for a r omega squared over here, then you get m r omega squared. So this is the equation for centripetal force. So you have two equations. By the way, this omega is the angular velocity, so we will see what that is. Alright, so this is what you will learn. This is basically what you have to know for this lesson on circular motion. Then the next is another topic, which is electric and magnetic field. So let's go through your book, and these are the answers to the textbook here. So we have circular motion. By the way, I have also uploaded a complete lesson for circular motion in the Cambridge A-level playlist, so you can go through that also, because the content is very similar. So what I'm going to cover here is basically the same content that you have for Cambridge as well. So you can watch that playlist, and I think that will also cover what you will have to know even under the Edexcel syllabus. So you can watch that lesson video also if you want. Anyway, we'll go through this book, but for that I'm using a separate book, which is the Cambridge A-level textbook. Alright, so circular motion basics. Now this is what we will be learning in this chapter. By the end of this section, you should be able to express angular displacement in radians and in degrees. Now you see, this is a displacement, but here this displacement is not a displacement that is measured in a unit of length. It is measured in a unit of angle. Okay, so actually it is how much angle an object that is moving in a circular path covers. So for example, if an object is here and then it moves to here, okay, so it's moving, the object is actually moving in a circular path like this. So let's say the object starts here and then it goes there. Now the center of the circular path is here. Then the displacement, the angular displacement, now from the name itself you can figure out angular, angle, something to do with angle. Okay, so the angular displacement will be how much of an angle it sweeps. So from here to here, it swept an angle, or it created an angle of theta. So this theta is the angular displacement. Now the theta can be either in degrees or radians. Define angular velocity. So once you have the angular displacement, and if you divide it by the time that it takes for it to go from here to here, then the angular velocity will be theta divided by t. Okay, so you can, I think it will be shown here, you see here, omega, that is the angular displacement, sorry, angular velocity, that is equal to theta divided by t. Theta is the angular displacement. So first thing is, you should be able to convert between radians and degrees, define angular velocity and make calculations using it. So you saw what that is. Then also, you see, define centripetal acceleration and derive and use the equations for it. So I showed you how to derive it. Now once you have the equation for acceleration, simply substitute that in the equation f equals ma. For acceleration, you substitute that, then you will get the centripetal force. Okay, so here this is actually telling you, I think, what is radian. Okay, for those students who are taking mathematics would have already learned this, because that is something you have to know for mathematics as well. So what is the angle in radians? This is the equation that you are going to use to define the angle in radians. So it is the arc length divided by the radius of the arc. Now let's say you have okay, the diagram is not given here. Maybe I can sketch that diagram. Alright, so here is the diagram. Now let's say this is the sector of a circle. So the object went from here to here. It covered an angle theta. And the distance that it traveled when it went from here to here is s. So that is the arc length. So the angle in radians is equal to s divided by r. Okay, the arc length divided by the radius. This is the angle in radians. So now if you consider a circle, okay, if I draw a circle, right, so this is the center. Let's say the object started somewhere here, so this is the radius r. Let's say the object started here, then it went all the way round this up to here. So the distance it traveled is equal to the circumference of the circle, and you have learned the equation for circumference of a circle, that is 2 pi r. So if we apply this equation for the angle in radians, this is the angle in radians, angle in radians, that is equal to the arc length. This is the arc length, you see the distance it travels along the arc length divided by the radius of the circle or circular path. So divided by radius. Now we will use this equation for this. So the object went all the way around from here to here. So the angle it covered will be then 360 degrees. So we will see the angle in radians then. So then theta will be equal to, the s will be 2 pi r, and r is still r, that is the radius. So then r and r cancels and you get 2 pi. So you see 360 degrees is equal to 2 pi radians. So you can write 360 degrees because it went all the way around, right? So it covered an angle of 360 degrees. So we can say 360 degrees is equal to 2 pi radians. Now here this is not actually a unit, but if you want you can write, if there is nothing written there, that means it is in radians, because if the angle is in degrees you have to write the degree unit there. But if the angle is in radians, then we don't need to write that because actually it's unitless. For example, if you take hertz, okay, hertz is what? Number of cycles per second. So here it's number of cycles per second. So we don't say cycles per second, right? We just say hertz. It's something per second, or number of rotations per second, revolutions per second. Similarly, this radian is, we can't say it's actually unit, so you don't even need to write it. But if you are writing, then we write it like a small c up there. Okay, for mathematics you would have learned this. That is how we write it. Or else you can write rad. Rad means radians. Or you can even write the full word radians. Or very simple, you can just keep it without anything. So if we divide both sides by 2, we get 180 degrees. 180 degrees is equal to pi radians. So we can use this conversion factor to convert between radians and degrees, or yeah. So if you have angle in degrees, for example, let's say you have 60 degrees and you want to convert it to radians, so then I will use this conversion factor. We know pi is 180 degrees. So if you want to find what is 60 degrees in radians, then you have this. So you can cancel the unit radians and also divide both by 10. So 0 0 cancels, degree cancels. Then we have, this is 6 into 1 and this will be 6 into 3. So this will be pi over 3. So what we just found is that 60 degrees is equal to pi over 3 radians. So like I said, you can use this conversion factor to convert between radians and degrees. And now you have learned what the unit radian is, and to find that, this is actually how you define it. Now let's go back to the lesson, main lesson. So you see, length of arc divided by radius of arc. So theta equals S over R, and this is what I showed you. So if it covers the full circle like that, then it travels a distance which is the arc length 2 pi r. It is actually the circumference of the circle. Then divide by r, the radius of the arc or circle, which is r. Then arc cancels, you get this. So this means that the angle will be 1 radian if the distance moved around the circle is the same as the radius. So if S is equal in length or distance to r, then you get r over r, which is 1 radian, just over 1/6 of the distance around the circumference. 1/6. Yeah, here it's 8 parts, right? 8 slices or 8 sectors here. Alright, then you can see the angle in degrees and the angle in radians. 0 degrees and equals 0 radians. 45 degrees equals pi over 4. But you don't need a table like this. You can directly use this equation, this conversion factor, and simply convert from radians to degrees or degrees to radians. And you can verify using this table. So you can try some angles, maybe 270 degrees, convert to radians. It should be this, like that you can try. I mean, I can just show you one more thing using the grid. Okay, I'll use another color so that it's easy to distinguish what we have done. Now if you take the quadrants, okay, the grid, okay, the quadrants, the mathematics students would have learned this. Let's say this is the first quadrant. Now we go anti-clockwise, we measure the angle positive anti-clockwise. So this is the second quadrant. This is the third quadrant, which is bounded by the negative x-axis and the negative y-axis. So here this is the x-axis, this is the y-axis, and here you have the fourth quadrant, which is bounded by the negative y-axis and the positive x-axis, this region here. Okay, so if you consider an angle from here all the way around here, that is 2 pi radians, right? You have learned, if you go all the way around from here starting all, that is 2 pi radians, which is 360 degrees. Then halfway is what? Pi radians. So pi radians is equal to, we saw here, 180 degrees, and you have learned about degrees, so you know, then from here to here it is pi radians. So it is equal to 180 degrees. Then what about from here to here? From here to here, that will actually be half of this, right? From here to here, half of that will be from here to here. So this is actually what, 90 degrees. Or we can also say, now if it's in degrees, you have to write the unit there, otherwise it will mean it's in radians. Then this will be what, pi over 2 radians. Then if you go from here all the way up to there, then you can see that here half plus half, that is 1, then plus another half, which is actually 3 over 2, 1.5. So half plus half is 1, then if you, this is another half, right? So then 3 over 2 or 1.5, 1.5 radians, and you know this is equal to, in degrees, 270 degrees. I'm just showing you this, but you can directly use this and convert it and see. And all the way around, you know, it's 360 degrees. Okay, so this is the conversion from degrees to radians, radians to degrees. Like I said, try a few examples, then it will be easier for you. And also we saw how to get the, what is the radian we learned, that is the arc length divided by the radius. So you can do some of the questions here and check using this table. Alright, then the next one is angular velocity. So now we know that angular displacement, that is theta. okay, and also that is the angle in radians. So how much of an angle it covers in radians is the angular displacement. See, angular displacement, now you know displacement is a vector. Angular displacement is the vector measurement of the angle through which something has moved. The standard convention is that anti-clockwise is a positive number. I showed that when I drew this. I told you we measure the angle anti-clockwise as positive. Standard convention is that anti-clockwise rotation is a positive number and clockwise rotation is a negative number. Okay, so now you learned what is the angle in radians, you learned what is angular displacement, you learned how to convert between radians and degrees. Okay, so you see alternative unit to measure angle, that is radian. So you have learned two units, one is degrees, the other is radian, but there's another unit, but we don't need to know those other units of measuring angle right now. Okay, so the next one is angular velocity. So angular velocity, we use the Greek letter omega. It's better if you are familiar with the Greek alphabet. Okay, there are a lot of videos also online about the Greek alphabet, and you can download the Greek alphabet from the internet. There are 24 letters in the Greek alphabet. Now you have both capital letters and simple letters. I think the ancient alphabet didn't have both capital and simple letters, but the new modern alphabet has, Greek alphabet has both uppercase and lowercase, capital and simple letters. So this omega here is simple omega. The capital omega is the symbol that we use for resistance, sorry, unit of resistance, ohm. So unit of resistance ohm, that is capital omega. Okay, if you look at the Greek alphabet, you will see all these letters, the capitals and the simple letters. So there are 24 letters. The first letter is alpha, then beta, then gamma, and the last letter, the 24th letter, is omega. So we use the simple omega. I can even quickly show you the Greek alphabet because we are using a lot of Greek letters in physics. Now if you are taking particle physics, okay, that is nuclear physics, you will have a lot of Greek letters that are used. So that's why it's better to become familiar with the Greek alphabet. I'll just show it to you quickly. So here is the Greek alphabet. Now you can see, like I said before, you have both capital and simple letters. So if you count 3, 6, 9, 12, 12 into 2, 24 letters are there. And you see both the capital letters and the simple letters are here. These are the capital letters and these are the simple letters. Then you can see omega, the last letter in the Greek alphabet. This is capital and this is simple. So this is what I told you before. This is the symbol of the unit of resistance, ohm. This is the symbol that we use for angular velocity or also angular frequency. Now if you take a simple harmonic motion, then there you have again this omega, but that omega, again the simple omega, but there it's representing angular frequency. So here it's angular speed or angular velocity under circular motion. Then you may have seen most of these letters. So here pi, in the O-level class also you have seen this pi, and I think mu. Okay, this is some people pronounce it as me, mu, some people mu. And for physics I think we pronounce it as mu. Then you remember unit of wavelength. Okay, symbol of wavelength, V equals f lambda, you had that. Then theta, we use this for angles. Eta, epsilon. I think in the AS lessons you learned this one, you would have seen this epsilon for Young modulus. Then delta, remember change, we use this letter capital, or sometimes we use simple also. If it's a small change we use simple delta, if it's a big change like that we use this. So alpha is the first letter, second letter beta, third letter gamma. Anyway, so now you have this, so you should know these equations. Now in the syllabus also they showed you those. See here, so let's see, omega, the angular velocity, is the angular displacement divided by the time. So you know this has the unit radians, this has the unit seconds, therefore angular velocity omega we'll have the unit radians per second. Radians per second. Okay, so it is actually how much angle it covers in the period of time. Then you have also learnt omega equals 2 pi over t. Now if you don't remember, how did we get this? So you can see the angle is 2 pi here. 2 pi means 360 degrees. So if something moves all the way around the circle, then it completes an angle of 2 pi radians. Now you have also learned the definition of period. Period is the time taken for one complete oscillation, revolution, cycle. Now in this case, one complete orbit, we can say, if it's like moving in or one complete a circle. So then what happens is, again now we can use the equation for angular velocity. Alright, so here I'll use a fresh page for this. Now let's say you know this equation already, you learned just now. Now if it covers and if it starts here, let's say this is the radius of the circle, it goes like that, then it covers an angle of 2 pi radians, goes all the way around 360 degrees. So the angle it covers is 2 pi radians. Now that is also the time taken for one complete cycle. So the time taken for one complete cycle is capital T, because that is the period. We use the letter capital T for the period. Period is the time taken for one complete cycle. So that's how you get this omega equals 2 pi over t. And that is the equation that you see in the book here. Omega equals 2 pi over t, cross multiply, then you get t equals 2 pi over omega. And you have also learnt frequency equals 1 over the period. You have learned this equation, f equals 1 over t. So if you replace t with f, okay, so if you replace t with f, then you will get this. Okay, I can even, it's very simple mathematics. So you have learned this equation, frequency equals 1 over the period. So I'll use a different color. So you have learned this equation, frequency equals 1 over the period, right? Now here you can see we can also write this as 2 pi times 1 over t. You can just take this out, right? So 2 pi and so on. Now what is 1 over t? That is f. So I can write, so this you can see, that is f, the frequency. So I can write this is equal to 2 pi f. So omega equals 2 pi f. That's how they get the other equation. Okay, then angular velocity, then instantaneous velocity. So again, from the name itself you can figure out what this is. Instantaneous. Instant means at that moment. So the velocity at that moment is called the instantaneous velocity. Now the magnitude of velocity is speed, so we can also have instantaneous speed. Now for example, let's say you are traveling in a car and you look at the speedometer. So at that moment the reading on the speedometer is the instantaneous speed. Okay, so because it is showing you the speed at that instant. So speed with a direction, that is velocity, magnitude of velocity, speed. So let's say you are traveling in a car that is going north, and at that it's not changing direction, it's going north, and at that moment you see that the reading on the speedometer is, let's say, 60 kilometers per hour. So then the instantaneous velocity at that moment, it's 60 that you saw, so it will be 60 kilometers per hour in the north direction. Because velocity is a vector, I mentioned the direction also. Okay, then now this you can see how you get this. V equals S over T. V equals S over T. Now what is S? That is the arc length, right? So if you go back here, remember this. This is the arc length, this is the radius. Okay, but here what we have is, okay, let's relate it to this part, because we want now the one thing is this, okay, omega, but we use for the tangential velocity, okay, I will, that is the linear speed also we can say. So what we'll do is, maybe we can draw another diagram. Alright, maybe we can use the same diagram. So let's say an object starts here and it travels to there. So the distance it moved, or the distance from here to here is, let's say, is the arc length. And you know v the velocity is equal to the displacement divided by the time. So let's say it took a time t to go from here to here. Okay, maybe we can also label the angle theta is the angle. Then it took a time to go from here to here, time t. So v equals s over t. Velocity is equal to displacement divided by time. Now this is not the angular velocity, this is the normal velocity, the velocity you have learned before. But the angular velocity for this case will be omega equals theta over t. So there is a difference, okay. Now this, you know, is in meters. So here the unit will be meters per second. Okay, so if you look at the unit, here the unit is meters per second. This unit will be radians per second. Okay, maybe I'll use brackets here to just show that is the unit. So don't confuse the two. So remember, angular velocity is angular displacement divided by time. Then you have the linear velocity. Now when it comes to circular motion, it's actually called the tangential velocity, okay. Now why do we say tangential? Because if you draw a tangent to the circle, let's say at this point you draw a tangent, so that is the v, okay. That is why we call it tangential, or we can even say just velocity. Okay, now in this case they say at that instant, so it's the instantaneous velocity. So we get v equals s over t, and then we have s is theta equals s over r. So s equals theta r. So this is how we derive the third equation. V equals r omega. Now we will also, I will also show you. So you have yeah, so previous page we have this theta equals s over r. So let's use that. So we have theta equals s over r. This is what we used to define the radian. Now what we will do is, we will make s the subject of this equation. S equals then theta r. So this theta r we will substitute for s here. So we get v equals, now remember the s, we substitute theta r for s, theta r over t. So that is the s there, okay. Then we will have, now theta over t, what is that? Omega. So we have v equals omega r. So all these equations are extremely important. Okay, so there are a number of equations you should know. So the very first one that we saw is this one, right? So that is one. Then we saw these two. Now this you have learned previously. In the AS syllabus also you have learned this, so you should know that also. So from this only we get omega equals 2 pi f. Okay, so this is also important. Maybe I will write it here. So we have omega equals 2 pi f, because this has omega and f, the frequency, 2 pi f. So this is normal frequency, okay, not angular frequency or anything. F is the frequency, omega is the angular velocity. Now in another chapter under simple harmonic motion or oscillations, you will see that omega is the angular frequency. sometimes students confuse that with this frequency. It's just this f is just frequency. Omega in a later chapter you will see is angular frequency. So you will be using the same equation, but the quantities that are represented by the equation are different. Same equation means the symbols will be the same, but they represent different quantities. Okay, then this you already know, the normal equation, displacement divided by time, that is velocity. So this, here we have this one. Then you have this, v equals omega r, very important. So remember, this is the normal velocity, not angular. Angular velocity, we'll write the unit here, omega. Okay, omega is the unit. Last letter in the Greek alphabet, the 24th letter. So you have this. Now, to help you understand this better, there is a question. In figure D, example rather, we can see a geostationary satellite orbiting the Earth. Now, what is a geostationary satellite? That is a satellite which is right above the equator. So, in addition to that, it will have the same period as the Earth. So, if it has the same period of orbit as the period of rotation of the Earth, then it will be always above the same part of the Earth. Now, for example, let's think of a country near the equator, maybe some African country or some Southeast Asian country, I don't know, maybe Indonesia. That would be like above the equator, right? So let's say this satellite is right above as Indonesia, and it's a geostationary satellite. So that means it will have the same period of orbit as the period of rotation of the Earth. So that means, now let's say this part of the Earth comes here, then this will always be above that, because this has the same period of rotation, period of orbit as the period of rotation of the Earth. So the Earth takes approximately 24 hours to complete one rotation. So you know, one day is 24 hours. That is the time taken for the Earth to complete one rotation. Now, since the period of orbit of this is also 24 hours, so when the Earth completes one rotation, the geostationary satellite completes one orbit. That's why it will be always facing the same part of the Earth. So if you have a geostationary satellite right above, let's say Indonesia, then the entire time it will be above Indonesia, even when the Earth is rotating, because this will also be moving at the same rate, will have the same angular speed, we can say, as this. Okay, geostationary satellite orbiting the Earth, what is its angular velocity? Now, to understand this, you should know what a geostationary satellite is, and now I told you what a geostationary satellite is. So angular velocity is omega, and then omega equals 2 pi over t. Now t is the period of orbit. So how long it takes to complete one orbit? That is 24 hours. So here you can see 24 hours is converted to seconds, because 60 minutes in 1 hour and then 60 seconds in 1 minute, or simply to convert from hours to seconds you can multiply by 3600. This is a simple unit conversion from hours to seconds. Okay, you should know this. If you have difficulty with this, you can write 24, write with the unit 24 minutes times 60 minutes divided by 1 hour, because 60 minutes in 1 hour. Then here you write 60 seconds per hour. Then you will see that the units cancel out and the unit that will be left is seconds. And in the numerator the unit is radians. Like I said, if it's radians we don't need to write the unit. So we have radians per second. So this is the answer. That is the angular velocity of the geostationary satellite. And we can also say that for something on the surface of the Earth, now we are on the surface of the Earth, let's say we are near the equator, so, or even if we are not, okay, so our angular velocity will also be this, because it is how much angle we cover in a certain period of time. So we will also have the same angular speed or angular velocity as the satellite, because we are on the surface of the Earth. and when the earth rotates, we are also moving with the earth. How quickly does a satellite rotate through a certain angle? If the radius of the earth is now remember, this is angular velocity or angular speed, but now this is v. This is the speed, okay, normal speed or normal velocity, because magnitude of velocity is speed. How quickly does a satellite rotate through a certain angle? How quickly, how fast, okay? If the radius of the earth is 6,400 kilometers, that is from the center of the earth to the surface of the earth is the radius of the earth, and the satellite in figure D, see this is figure D, is in orbit 35,600 kilometers above the earth's surface. So from here, the surface of the earth to there, that is the altitude, is 35,600. What is the velocity of the satellite? Now here it doesn't say angular velocity, so it's just the normal velocity, which we say v. We use the symbol v. So we can use the other equation. Now what is that equation? This one, v equals omega r. We found omega. Now we know what r is. Remember, r is from the center of the earth to the satellite, because this center of the circle is here, circular path is here, that in which this is moving. So we have to take it from the center of the circular path to there. That will be the radius, not from the surface of the earth, okay? So then you have to add the radius of the earth and the altitude, that is how far it is above the surface of the earth. That will be your r. Then omega you found previously, so you get the speed to be this. Now remember, for us it will be much lesser, because our radius will be the surface of the earth. So for the satellite, in addition to this, it has this. So if you want to find our speed, the speed, because we are on the surface of the earth, then our speed will be our velocity or our speed v will be 6,400 times this value, okay? Because we don't take this, because this is because it is above the surface of the earth, but we are on the surface of the earth, so this altitude is 0. Okay, so now you learned about instantaneous velocity. You learned this other equation that has omega and f. Now we have centripetal acceleration. So basically here what you need to know are just two equations. One is this, a equals v squared over r, and the other is a equals omega squared r, or r omega squared. So I'll just write those equations also. Alright, so for centripetal acceleration, there are just two equations like I mentioned, and you have to know those two equations. I will show you, it's written here. So one equation is the centripetal acceleration. Now this is not the normal acceleration, okay? So it's centripetal. I'll use a small c here to indicate it's the centripetal acceleration, okay? So I don't need to use different colors, so I'll just use the same color, okay, just to avoid any confusion with the normal linear acceleration. So the centripetal, c for centripetal acceleration, is equal to v squared over r. Now remember, this is the speed or velocity, and then this here is the angular speed or angular velocity, because magnitude of the velocity or angular velocity will be the speed or angular speed respectively. So then you have that. So you should know this. Now what you see in the book is the derivation of this, but what you will have to be actually use are these two equations. So to keep it simple, you should know how to use these equations. Now let's go through this example, and then I will go through this long derivation. What is the centripetal acceleration of the satellite in figure D? Okay, so now simple, we can directly use the equation a equals v squared over r. Now if we use this equation also, we should still get the same answer. So v is the tangential velocity, or that linear speed. They also, I think, call it the instantaneous speed here. Then that is 3050. So it will be 3050 squared divided by r. R is the radius of the circular path. So radius means from the center of the circular path in which it is moving to the arc of the circle in which it is moving, which is the radius of the earth plus the altitude. That will be this plus that, right? 35,600 plus 6400. Now remember, this is in kilometers, so to convert to meters you multiply by 1000 or 10 to the power 3, then you get this. Similarly, we can use A equals r omega squared, then r again is that same radius, and omega is that, okay, that value there. So you see, and then you get the same answer. So these are the two equations you should know for centripetal acceleration. Here is this and this, both are centripetal accelerations, not the normal acceleration. Okay, that's why I use a subscript C here, so that you won't have any confusion. Now if you look at this diagram, that is actually showing you how to derive this equation. Velocity is a vector. Vector have both magnitude and direction. An object moving in a circle may travel at a constant speed, at a constant angular velocity, but the direction it is moving must constantly change. So it can have a constant angular velocity, it can cover an equal angle in an equal time period, that is a constant angular velocity. But the normal velocity, the velocity is not constant, because every time the direction is changing. This means it is constantly accelerating. Okay, so it's moving at a constant speed in a circular path, so it will have a constant acceleration, which is what we call the centripetal acceleration, and this centripetal acceleration is directed towards the center of the circular path in which the object is moving. So if I draw a circular path like this, and let's say the object is here, and let's say it's moving that way. Now this is the center, let's say. So here we have the direction of the acceleration is directed towards the center of the circular path. So always, even if it is here, for example, the centripetal acceleration will still be directed towards the center of the circular path. And according to Newton's second law, F equals ma, the resultant force produces the acceleration, and the acceleration is in the direction of the resultant force. So I will use an arrow to indicate that they are vectors. So then the centripetal acceleration will also be towards the center of the circular path in which it is moving, because this force and acceleration should always be in the same direction. Alright, so here you can see now this is the velocity v, okay, it's in that direction. When it is here, it's in that direction, always at a tangent to the circular path. Then you can take the components of the velocity in the vertical and the horizontal direction. So in the AS class you have learned trigonometry and how to resolve vectors. So if let's say this is the angle theta, then if you resolve it this way, it will be v cosine theta. It sweeps the angle, so we take cos. If it's perpendicular to that side, it will be sine. If you can't see this, you draw a triangle, right angle triangle, and then use trigonometry, sine, cosine, tan. Then you will see this side of the triangle. If the hypotenuse is v, then the adjacent side will be v cosine theta. Similarly, this will be the opposite side to this angle, which is equal to that side in length. That will be v sine theta. So when it is here, the velocity, the component of the velocity in the horizontal direction is to the left. The component of the velocity in the horizontal direction here is to the right. So v is that way. Here v is more to the left. Here is v is more to the right. But the vertical component of velocity is the same. But the horizontal components of velocity are in opposite directions, which means there is a change in the velocity, which we call acceleration. So in the vertical direction, the acceleration is 0, because you can see the vertical component of the velocity before and after is still the same. Then if you take the horizontal direction at A, if you take to the right as positive, it will be v sine theta. Now here it is to the left, so that's why it's minus v sine theta. Then the acceleration will be change in velocity over time. So final velocity minus initial velocity divided by the time. So it will be, let's say the difference of this, that will be this change in velocity. So it will be 2v sine theta divided by t. Then v is equal to Remember S over T, I showed you that earlier. Okay, and then we saw that S is theta r, so then we got this V equals theta r over T, V equals theta r over T, theta r over T. Then if you make T the subject of the equation, you get this. Now angle moved in time T is labeled as 2 theta. So from here to here, the time is from there to there, and the angle it covers is 2 theta. So we have that, and now we can see the acceleration. Even when we calculated this theta, remember how is this angle here equal to this one here, and how is the angle here equal to that angle there. Okay, so it's again simple mathematics. I think if you have taken mechanics and those mathematics, you will be able to figure this out. Okay, so it's like this. Now let's say you draw a vertical line here. Okay, or you can also think of it like this. Now see, if you see the angle here and the angle here, okay, if you extend this arrow, or if you draw a line along this arrow like that, then the angle here and the angle here are the same. They are alternate angles. Okay, then here you see this is the perpendicular to the radius, so that means this angle here is 90. So 90 minus theta will give you this. Again from here to here you are doing 90 minus this angle, which will again be equal to theta. You can figure that out. You can draw a large diagram and you can see this and this, they are equal because they are alternate angles, and this and this, the angle between them is 90 degrees. So then this minus 90 will give you this. Again this and this, they are perpendicular to each other, so again you are doing 90 minus of this, which will give you again theta. So you can figure that out, you can draw it and try it, you should get it. Okay, so we have that. Now we have this. Now remember, this time is twice the time, twice the angle, so it will be 2 theta. Then the acceleration you substitute here for t. This is what you have for t. Then we get this equation, simplify, then we get this one. Now you have this must be true for all values of theta, and as we want to find the instantaneous acceleration at any point in the circumference, we must consider the general answer as we reduce theta to 0 in the limit as theta tends to 0. So at every instant we are seeing this, so the theta is very small. So then sine theta divided by theta equals 1 when the angle theta is very small, or when theta tends to 0. If you have seen the sine graph, you can see it from there also. So then we have this equation for acceleration. So this, you see here, v squared over r, and you can see this is directed towards the center of the circular path. And we have seen this v equals omega r. So if we substitute that here, we get omega squared r. Remember what we saw earlier, v equals omega r. I showed you how to derive this. So for that, for v we substitute omega r, so we get omega r whole thing squared, this one, then we get omega squared r, this one. Okay, so that's how you get the two equations. But what is most important is to use the equations. You remember them and use them. Okay, now finally, these are the definitions, and these are what we learned. Okay, so if you look at the pages here, we learned about the radian, we learned about angular velocity, and then we learned about centripetal acceleration, and one more thing, angular displacement also we learned. So you have to know these definitions, because in the exam they can ask you this. Okay, so here we have the angular displacement, okay, this one, and yeah, so radian and angular displacement. Okay, then angular velocity, centripetal acceleration, you should know these definitions. Angular displacement is the velocity measurement of, vector measurement of the angle through which something has moved. Now you should know these definitions, because if you try to write in your own words, you might miss certain keywords. So best thing is to memorize it and write it with understanding. is the vector measurement of the angle through which something has moved. Angular velocity omega is the rate at which the angular displacement changes. Unit radians per second. Unit is radians per second. Rate of change of angular displacement. Centripetal acceleration is the acceleration towards the center of a circle that corresponds to the changes in direction to maintain an object's motion round that circle. Okay, then the final topic here is centripetal acceleration. Now this also is very easy. Centripetal force, again this is very easy. What you are supposed to know here, like I think I said, is that from F equals ma you can get this equation. So basically it's a matter of using the equations. I told you here the direction is towards the center because of the equation F equals ma, Newton's second law. The resultant force produces the acceleration. So in this case the centripetal force, I will use a small c for centripetal, will be equal to the mass times the centripetal acceleration. So the centripetal force is mv squared over r. Then we have m omega squared r. Now how do I get this? Because a is what, v squared over r, and also a is omega squared r. So that's how we get the two equations for centripetal acceleration. This is one, this is the other one. Okay, so they are showing you how to get that, which is the same thing I showed you. So one equation is mv squared over r, the other one is m omega squared r. So from this equation you can see the resultant centripetal force needed will be larger if the object rotating has more mass. Now see, if you look at let's say this equation or even this one, the greater the mass, the greater will be the centripetal force required to keep it moving in that circular path. Now if the speed is greater, then the centripetal force needs to be greater to keep it moving in that same circle with the same radius. The object is further away from the center of the circle. So if r, the centripetal force needed will be larger if the rotating object has more mass. The object rotates faster. The object is further away from the center of the circle. Now from here you can see if r is greater, then f will be greater. So if it is moving at the same speed in a larger radius, to maintain it moving at the same speed, then you will need a larger force. Okay, so here is another example. Estimate the centripetal force of an astronaut. Now it's a matter of simply using the equation. Okay, so F equals m omega squared r. Estimate the centripetal force on an astronaut in the astronaut training centrifuge. Figure B, this one. The astronaut, there is an astronaut in here, and this thing is rotating. So when it rotates, there will be a centripetal force on the astronaut. So people can feel dizzy when they do this. Okay, I have seen some documentaries on, I think, Discovery Channel. Okay, and I saw this done on the astronauts. You can also see it. I think that is there online. If the capsule rotates once every 2 seconds, so the period is 2 seconds. Once every 2 seconds, you can see it completes one rotation in 2 seconds. Estimate of the radius of revolution r equals 6 meters. Yeah, so this is about, I think, the estimate, because it's an estimate, right? 6 meters. Estimate of astronaut's mass, so a person can be weighing about 70 or 80 kilos. Then the velocity is 2 pi r over t. Remember, 2 pi r over t. So 2 pi r is 6 over the period is 2. So we get this. Then centripetal force is this. M is the mass of the astronaut. V is 18.8. Then R is 6. So we get this. So this is about 6 times his weight. So he will experience a force about 6 times his weight. So if the operator of the centrifuge were to increase the rate of rotation to once every second, so it takes 1 second to complete one rotation. what would the astronaut's angular velocity, centripetal force and acceleration now be? So angular velocity, very simple, you can find from this, omega equals 2 pi f. Now the frequency is what? 1 rotation per second, so 1 hertz, right? So it will be then 2 times pi times f. So you can try that, 2 times pi. You can even use your calculator right now and try it. So it's 2 pi, which is 6.28 radians per second. Then centripetal force, we have this m 80 r6, and this thing you have that. Centripetal acceleration, so you see it's very easy, right? You can find it. This is about 24 times the acceleration due to gravity and would most likely be fatal if maintained for more than a few seconds. That's why I told you people can feel dizzy if they do this too fast. Similarly, like for example, if you're in some vehicle that is moving very fast at once, again you can feel dizzy at times. Okay. Especially in these amusement parks, they have these like extreme rides on roller coasters and other machines. So some people, they faint because of that. Anyway, so finally these are the equations. So you can see all the equations here. This one we learned, this one, this one, this one, this and this. So I think it's showing you all the equations that I wrote down. And remember this also. Okay, then this final part is to figure out the centripetal force. Now, like I mentioned before, anything that is moving in a circle or circular path will have a centripetal force directed towards the center of the circular path, and the centripetal force is the resultant force. So it's the sum of the different forces, we can say. If there is more than one force, it will be the sum of those forces. So in this case, the centripetal force, it's just one force, which is the tension in the string, which is keeping this rotating. So here you can see the diagram. It's going in a circle like this, and the centripetal force should be always towards the center. So what is the only force here? We assume no air resistance, then that will be the tension in the string. So what keeps this moving in the circle is the tension in the string, because if the string is breaks suddenly, then it will no longer go in the circular path. So we have this equation, then omega equals that, omega squared. A graph of omega squared plotted against f should give a straight line, best fit line. Okay, so why? Because m is constant, m is the mass, r is constant, r radius and this. So when if you keep the same radius, okay, so here let's say this is the length of the string, you can't change it. So if this moves faster, the force on the string will be greater. Okay, so if you move it very fast, then the string may not be able to bear that force, it might snap or break. Alright, so centripetal force is the resultant force towards the center of the circle to maintain an object's circular motion. Again, these definitions you see here in red are very important. Make sure you memorize them with understanding. And I think that's the end of the lesson. Make sure you answer all these questions, including the questions which were throughout the chapter. Go through those examples, then do the questions that follow them, and make sure you answer all these questions as well, the end of chapter questions. So you may have to figure out what is the centripetal force. Okay, it can be just one force, it can be the resultant of more than one force. So you have to be able to figure that out. And that is the end of that. Now, one more thing, we'll quickly go through the revision guide. So here is the revision guide, and it's also in the same order basically as the order of the chapters in the textbook, because this is like a summary or like the notes that you need. So if we go through this revision guide, let's go to circular motion. So this is what we saw. V equals 2 pi r over t. Because why 2 pi r? Because to complete one round, it has to travel a distance equal to the circumference. So V equals S over T. Remember, the circumference, the arc length divided by the time. So if it goes one whole round, then it will be 2 pi r, which is the circumference. And the time taken for one complete round is the period, which is capital T. Then we have the angular displacement. So we have angular velocity then. See, everything is clearly shown here. then we saw V equals omega or this thing, and now there are some examples here. Make sure you do these examples. And here we have centripetal acceleration, then some worked examples, and make sure you do all these questions and check the answers. The answers are at the back of the book. So here we have centripetal force. Now we have this equation, so some worked examples are there, and here is another worked example. So this is where you have to figure out. Now here you have the force this way and also the weight force. So the resultant force is actually that one. Now if it's moving with constant speed, then for it to move in a circle, the centripetal force should be this way, which will be the component of this lift force in this direction. So you have to figure that out. So you see, this is L, this is theta, right? So L sine theta will be the component this way. So what balances the weight is the L cosine theta. L cosine theta equals the weight. L sine theta is the centripetal force. So this aeroplane is moving in a circular path like that. So it goes like this, goes like that, and then comes back. So going in a circular path. So you have to figure things out like this, which is the centripetal force. Alright, so that's the end of that lesson on circular motion. So there are a lot of questions here. Make sure you answer all this. First you can start answering all the questions in your textbook, and then also you can answer all the questions in the revision guide. Okay, so now you can again go through the syllabus to ensure that everything was covered. So we learned this 87 conversion between radians and degrees. Then we saw these equations. We learned the equation for centripetal acceleration. So for something to move in a circle, there has to always be a resultant force towards the center of the circular path. That is what we call centripetal force. And finally you had the equations for centripetal force. So you get that from Newton's second law. I wrote them down here as well. Okay, so that's the end of that lesson on circular motion.